Good afternoon. My name is Scott Deaton. I am president of Dataforensics. We are a geotechnical data management software company. We founded the company almost 19 years ago now with the fundamental premise that you should only have to input your data once. You should be able to use that data many different ways for many different purposes, but input your data once, and ideally that data should be input digitally as close to the source of the data collection as possible. So whether that's on tablets in the field, whether that's getting your laboratory data automatically imported from automated data acquisition systems into a lab management system, whether that's getting your in-situ testing data imported into a database so that you can use your borehole and in-situ testing data and lab testing data together. It's all about having all of your site investigation data together in one single environment where you can use it however you need to and transmit it to whomever you need to transmit it to in a standardized format. So obviously geotechnical data interchange is a big part of what we do. Let's talk about technology in general and what are we experiencing other than the novel coronavirus. So we all probably have one of these devices either in our pocket, at home, or both, whether that's Alexa, Google's Assistant, Siri, Microsoft's version with Cortana. And one of the things that all of this technology has in common is it's driven by AI and big data. Just a simple example, whenever you have Alexa tell jokes, they record the responses to determine what people think is funny and what is not funny. And they're using that to improve Alexa's joke-telling ability. Now, AI and big data is obviously, there are countless possibilities of what that can do in the industry. But let's go back and let's talk about what is AI and when was it developed, and look at a little bit of history and timeline. So back in the 50s, Alan Turing determined a test to determine whether a machine is actually capable of intelligent human behavior or not. In the 60s, we had some robotics work happening that was using AI. Then there was a big gap. Not a lot happened for really 30 plus years. And that's the one that I remember quite vividly. I was a senior in college at that point, and IBM's Deep Blue computer beat world champion chess player Garry Kasparov. And that was a pretty big deal. Pretty cool stuff. Then there was kind of another gap where there were really about, another 10 years before much of anything was done again. And part of that's because what we found is that AI takes a lot of data, so you need a lot of storage, and it takes a lot of processing power to do it. And really until about 2009, that was somewhat limited in comparison to what we now have the capability of doing today or even 10 years ago. So that's when Google started building self-driving cars. And a couple years later, IBM Watson beat the Jeopardy champions. And you remember that first game, if you saw it, didn't do very well. And once it figured out how to play against a real person who was a world champion, then it came back and just annihilated the guy. It was quite interesting. So if you haven't seen that, definitely some interesting binge watching you could do while you are on your Corona vacation. So that was 2011. Now in 2016, Google's DeepMind AlphaGo beat the world champion in an ancient Chinese game of Go, which if you're not familiar with that, I obviously don't know how to play it. That's way above my pay grade. It is the most complicated game in the world. The number of possibilities of moves is more than the number of atoms in the universe. So Google actually started working on that in something like 2014, I believe. It took them 18 months to 24 months to actually get it to the point where the computer could beat a professional Go player. And that's what I want to focus on because that's kind of interesting. So it took them 18 to 24 months to do that initial development where they trained a computer on how to win at Go. Then they said, well, let's have AlphaGo Lee, the one that beat the champion, teach another AI system how to play and beat the game Go. It did that in 3 days. In 21 days, it had reached a new level of AlphaGo Master, defeated 60 professionals online. It has become the best Go player in the world, and it's all from self-play with no human interaction, no human intervention, historical data. So it turned the strategy of Go on its head with new winning moves that had never been utilized before by humans. It had no preconceived notions about how things were supposed to be, how they were supposed to behave, what you were supposed to do. And that was all based on data and looking at data in different ways. So let's transition to our geotechnical world. If you can process it into one or more formats without re-inputting it or without using multiple cut and paste operations, you have data. This is really important. Geotechnical engineers, in many cases, are not managing data. Most DOTs that require that you give them subsurface information in their own proprietary GINT formats, that's not data. They're not managing data in most cases. In some cases they are, but in most cases they're not. When we talk to organizations, we also hear, oh yeah, this is what our geotechnical archive looks like. Boxes and boxes of paper-based reports. That's not data. A lot of great information in there, but it's not data. Data is really the key. PDF borehole logs. Those are not data either. If you're going to reuse this data, you're going to have to do something. You're going to have to type it into some other system. Not data. So why do we care about data? Let's say I'm a consultant. How would you feel if your boss told you that you needed to retype the N values for all of your boreholes on a project 10 times? Well, first of all, you'd probably look at your boss like he'd lost his mind, which he might have if he did ask you to do this, so that'd be a fair assumption. But then you might think, well, how reliable would that data be? I've got 10 different sets of the same data. I've retyped it 10 times. Which one is correct? How many errors would there be? Very good, valid questions. So there are some experts who have looked at human behavior and type rate, and what they have found is that there's typically a 1% error rate for expert typists. So if you're not an expert typist, then you probably have a higher rate than that. I give you that example because fundamentally, what people are doing in the typical workflow of geotechnical data is they are retyping subsets of the same data 10 times, just like that previous analogy that you probably thought was completely ridiculous. So let's look at the typical workflow for a site investigation project. You start off, you lay out your borings in CAD. So you input your borehole IDs once. You then export that to a KML file, and that is using Data Interchange. So KML is a form of data interchange, of spatial data. So that's great. You can look for obstacles in Google Earth. You can take that same KML file, put it on your phone, and actually go locate the boreholes on your phone out on site. Now, we're going to then drive a stake into the ground, and we're going to label that stake with the same borehole ID we wrote up here. And then when we're doing our boreholes, we're going to have to write our sample labels, and we're going to handwrite our field logs. So project IDs, borehole IDs, sample IDs, depths, going on both of these steps. Now we've finished our data collection in the field. We come back to the office, or we send that back in. Somebody is going to have to type that data into GINT or some other system, whatever you're using, GINT, whole-base, logplot, whatever it happens to be. Then you're going to manually have to type up a test schedule of what laboratory tests should be run on which samples that were obtained back in this process. So we're going to rewrite project IDs, borehole IDs, sample IDs, depths once again. Now, while the lab testing is going on, we may get those location coordinates from the survey, and that was digital, but it was in a format that we couldn't actually get into GINT. So we get to type those coordinates in. And if you've ever typed in latitudes and longitudes down to 6 decimal places, obviously that can be fraught with error as well. Now, we're in the lab, and we've gotten our test schedule. We're performing some testing, and so on each test sheet, where we record Atterberg limits or grain size or proctors or CBRs or triaxials or whatever it is we're doing, we have to rewrite those same sample details, project ID, borehole ID, sample ID, depth, once again. We then write the results on the handwritten sheet, and we have to transcribe that test data into something to do the calculations. So we're going to do that in Excel. But then we want to summarize that data in a nice tabular summary, so we're going to retype that. And then lastly, because we want some of that data on the borehole log, we have to transcribe that data one more time to get it into GINT, so we can plot it on logs and on sections. So 11 times we're re-inputting subsets of the same data for a typical workflow. Now, this isn't something we made up. We interviewed many consultants who work for Ohio DOT, and this was the most efficient consultant. The least efficient was actually 15. And if you then account for the fact that every time we're doing a different lab test, so if we did an Atterberg, a grain size, and a hydrometer on 3 different test sheets, we're rewriting that same data 3 times. So really, this 11 is more like 14, 15, 16, 18 times. It's pretty astounding. So obviously, that's causing some issues. Okay, so let's say you have a small site investigation project. You've got 5 boreholes, 1 sample in each borehole, 3 laboratory tests on each sample. Going through that workflow we talked about before. If we just dive in and we look at one aspect of that workflow more closely, here you see kind of what I was talking about. Project ID, borehole ID, sample depth. Then you schedule the moisture content, the Atterberg, and the sieve. So you're doing that. Then we have our project ID, boral ID, sample depth that we're writing on the lab sheet. Then we're doing our masses and our other test data for transcribing that into Excel. Then we're rewriting all of these again on that summary, and we're transcribing that same data again into Gantt, and where we just have to add the results. So really, it's actually just to complete that small hypothetical scenario. It's 21 times re-inputting some of the data. Re-input 5 times, 105 pieces of data that have been repetitively input. The standard error rate, one of them is probably incorrect. Which one? So obviously you have to spend the time to ensure that doesn't happen. That violates our first golden rule of data entry. You should only have to input your data once. As I mentioned, that's what we founded our company upon almost 20 years ago. Second rule, get somebody else to do it. That doesn't mean give it to your colleague and just pawn off your work on them. It means if it has been created somewhere in the workflow before, you shouldn't have to input it now. So it should just flow through your process and your workflow. The third golden rule is also a very important one, and as people have been moving away from Gantt to the whole-based platform, they're finding that they're often not managing data, and they're inputting multiple pieces of data into the same field, because in Gantt, everybody created their own database structures, which was in many cases not managing data. And then when they want to actually manage the data, then they're like, oh, really? We had a field where we put 3 blow counts in one field. Oh, that's a problem. We want to put that in separate fields in the database. We have to make some assumptions. How did we put that multiple pieces of data in the same field, which is then problematic. So don't do that. It just makes your life difficult. Violates rule number 1 in actual database design. Let's move along to data interchange, and how are those useful? And what are they? So fundamentally, what a data interchange standard allows you to do is that people who are producing data can use the software and the platforms that best fit their needs, but they can create a standardized output file that then anybody else who wants to consume in some other software package can import that standard file. It's very much like DXF is for CAD. So DXF is drawing exchange format. What we're talking about here is a geotechnical exchange format. So basically it means it's software independent. You can do your work your way using the tools that best fit your needs, and other people can use theirs. So what that means is that fundamentally you could be using data forensic software, and we generate a DIGGS file. That same file could be imported into KeyLab or Wholebase or Gantt, or Geotech could produce files from their laboratory testing equipment, and that could be processed in whatever system wants to import or export that data. Same thing with instrumentation. So it's all about making your data accessible without having to do a lot of data manipulation is really what it comes down to. Who are some geotechnical data producers? Obviously people who are working in the field. You've got people doing classifications of soils, whether that's in the field, that's in the laboratory. Anytime you're doing any kind of testing in the field on the lab, that would make sense. You have design personnel who are involved in that process as well. And then you have scenarios where sensors are creating data. Obviously, they are producing that data. So all those people produce data, and then they may need to consume some of the same data generated by one of the other people in their process. So who are some examples as organizations of data consumers? Well, obviously, DOTs are a big consumer. Large commercial industrial clients are the Army Corps of Engineers. When we think of DOTs, you may have a geotechnical division, but you have other departments within the DOT who want to utilize some of the geotechnical data. So it might be pavement design, it might be management, it might be bridge design. All kinds of different groups want to have that geotechnical data, and so they have their own custom systems, which would mean you'd have to re-input that data in your system and then in their system. I've actually worked with DOTs where literally they're re-inputting the exact same data in 3 or 4 different systems, depending on who wants it. Contractors, obviously those are consumers, potentially consultants. They would love to be consumers. In many cases, they can't be because they don't have access to historical data. So let's look at what happens today on a typical project, and let's use a large highway project where you've got an engineer, you have the client who's the DOT, that's why the box is in red, because they're the client, and maybe there's a regional archive that has historical data, maybe there's not. In most cases, there's not, but we'll assume there is for this scenario. So the engineer defines the site investigation plan, sends that to the drill crew. The drill crew has to send data back to the engineer. And so you have to agree upon what format all of these data interchange are going to happen on a project-by-project basis, because there is no standard database structure for GINT. There's no standard way people are working in geotechnical engineering from a data management perspective, unless you're using Wholebase. And then there is, or you're working in the UK or Australia, and there are standards there that are defining essentially how people should be doing this. But in the US, in Canada, we're not. So on every project, we essentially, for every one of those data transfers, we have to define what does that format look like. So we reinvent the wheel on every single project. It's obviously good for the consultants who are getting paid by the hour, not so good for the clients who are stuck with a very large bill because people are having to reinvent these data transfers on every project. Now, if we expand upon this and you have that one client who works with 3 different engineers, and each of those engineers works with different drill crews in different labs, then really we have 15 stages of data transfer because we have now 3 times the number that we had before. Obviously, you can see this is not sustainable, but that's what we're doing today. Not ideal. So the goal of DIGGS is that you can be doing your on-site logging in tablets, transfer it via DIGGS to your boring log software, to your laboratory software. All of these systems can communicate together without you having to re-input that data. So you can streamline your internal processes. So what are some benefits? Well, we've talked a lot about what it is, but what do I get out of it? That's the point of the presentation. Benefit number 1 is consultants can get data from their clients, the DOTs, the Army Corps of Engineers, other teaming partners. So you can use that data without having to re-input it. The number of projects we've been engaged with to help clients with data migration to get it into a standardized format so that they can actually use it on some of these large projects is crazy. Obviously, you reduce your costs because you can literally just import a file, and now you can analyze your data however you want to, whatever your system is set up to do. Eliminate your redundant data entry. Obviously, fewer errors means you have reduced cost, and now we're also introducing reduced risk. That's a good deal. Lower liability, that makes everybody happy. You can optimize your internal processes for producing data. And what that means is that if you work today, if you work for Virginia DOT and North Carolina DOT, South Carolina DOT, and PennDOT, and Kentucky Transportation Cabinet, and Ohio DOT, you have to do your process for doing a borehole and the associated lab testing 6 different ways, in addition to the way you manage your data today internally. So 7 different ways, really. So you can't have a standard process. With Data Interchange, you can. You can have your process. You can optimize that process to the best of your ability. You can make it as efficient as possible, give them the most reliable data at the lowest cost, reduce your risk. And to top it all off, you can do more analysis and design instead of manipulating your data 10 times, 15 times, 21 times. So what are some other benefits? Let's look at other people who would be those consumers. Well, there are benefits to contractors. Today, contractors do not get data, unless it's a design-build scenario. They don't get data to do their bid submissions. They get PDFs of plan sheets and tables and things that they can use to create their bid submission, but they don't actually get the data. Because they have all this data, they can create a more reliable design. It's actually safer, more robust, and use more reliable construction techniques because they have a higher level of certainty because they have larger amounts of data and they can quantify uncertainties. They can develop more reliable bid submissions because they have all this data available, so that's going to result in fewer change conditions, fewer litigation-related expenses. Everybody loves that. And then AI and data mining. Using big data tools, they can data mine and apply artificial intelligence to improve estimates and construction plans. So what are the benefits to owners? Owners are the ones who obviously get the most profound benefits, but everybody gets some throughout the process. They get more reliable data that's provided to them, so they can use it and reuse it. Don't get worried that just because the DOTs are going to have all this data means you're going to actually be doing less drilling, because that isn't what we found happening in Australia, in the United Kingdom, in Hong Kong, in Singapore, where they've been using data interchange standards for the last 20 years. What we found is that people are actually optimizing their site investigations, targeting areas where they aren't as certain about what the material properties happen to be. So they're targeting new boreholes to better fill in their knowledge gaps. So just because you have more data doesn't mean you're going investigations. Obviously, we talked about contractors can actually use this data so they can optimize the construction, reduce risk, and make it safer, more reliable infrastructure. Huge benefit to owners, obviously. Internally, some DOTs actually are data generators as well, so they get the same benefits consultants do, where they have the fewer errors and reduce the cost of internal processes. It also allows them to integrate with other software versus having to retype that same data 3, 4, 5 times into different systems that different departments within the DOT need to utilize. Owners can manage risk better by using data. So whether it's looking for a problematic shale layer that has a certain slate durability index that keeps causing rock falls along I-64, or it's some kind of slope stability analysis based on some other formation that is known, whether it's liquefaction related, whatever your geologic hazard of interest, karst, whatever it is, you can use data mining, AI, and machine learning to help manage your risk. There's that old saying, if you can't measure it, you can't improve it. But using data allows you to better manage your risk, whether that's your operational risk or your construction risk. And when you're looking at the risk, it could be those different types of vulnerabilities, like I mentioned with the slope failures. You combine those properties with slope geometry that could also be digital data, DEMs, and you're then starting to have very large, robust data sets that you can start looking at, whatever it happens to be. You can combine it with real-time instrumentation data, with your geologic data, with seismic data, with whatever it happens to be that's important to you and your type of work. A study from the National Economic Development Office in the United Kingdom found that 50% of their projects overran by at least a month, while a little over a third of them were due to ground problems. That's pretty telling. So if we can improve that just a little bit, then you can improve your time overruns and your cost overruns. Another report from the UK found that 70% of public projects were delivered late and 73% were over the bid price. So it's all about using data more effectively to help minimize those cost overruns and delays. And where we are as an industry today is we're very much in the reactive phase. As we have more data and we adopt technology, we can move up that curve to proactive and predictive, where we can actually begin using AI and big data to help make better decisions, lower our risk, increase our reward. It's a very telling slide from almost 13 years ago, but it's all because of data. So let's give some examples. What are people doing with their data today? Clients are using their data in ways that they couldn't do 5 years ago or 10 years ago to improve their data collection process and better train employees. We've got clients who are improving their analysis capabilities and improving visualization capabilities. And those are all data-driven. So let's use a very simple example. A simple chart that's actually Excel hooked up to our enterprise cloud-based database. What this allowed our clients to do, and we've been having people ask us this for years with Ghent, can you create a table like this which will show us where we have a problem between how we classified it in the field versus how it was classified by the lab. So we can then go back and easily correct and QA our logs and make sure that our field classifications make sense based on the lab test results. Literally took me 5 minutes to create this table in our enterprise cloud-based system. It would have taken me 2 weeks in the old antiquated Ghent system. And because there was no standard database structure, if you're working for those 3 or 4 or 5 or 6 different DOTs that mandate you must do it their way, then you would have to build that same report 6 or 7 different ways. And in many cases you can't, because you're actually prevented from modifying their structure. You can then go a step further where you say, well, let's look at how logger A and logger B is doing it, and looking at maybe if you did actually follow ASTM D2488, which we certainly encourage following the standard, where you estimate the percent sand, fines, and gravel to the nearest 5%. You can then actually say, you know, the guy in the field logged it this way versus in the laboratory it was a different way. And what's the difference between them? So you can then say, well, you know, logger J. Jones, he was typically off by about 10.5% on the high side, and logger A. Abrams was off by about 16% on the high side. So you can help your people dial in how they're classifying soil in the field. Here's a scenario that one of our clients, you can see they've drilled almost 49 miles since they've been using our software in the cloud, 1,640 projects, range of borehole depths, whether they're hand augers, test pits, boreholes, CPT soundings, boreholes, and rock coring. Got it on a map as well. So you can see the location. So they're using this as a management tool to see what's going on in our company. How many boreholes have been logged? Who's the top logger? Well, Jay Carlton, man, he's a rock star. He's over 500 boreholes he has logged. Then they dive in a little deeper, and they started looking at specific data that they wanted to identify where they are not following what they should be doing. So every borehole should have a coordinate. It was drilled somewhere on this earth, presumably, and we need to know where that borehole was located. Company policy. So out of 12,457 boreholes, we had almost a quarter of them had no borehole coordinates. And you can then look at who are the employees who are not actually recording those coordinates properly. You can then address that through training to improve your data management process going forward. Dr. Robert Liang at the University of Dayton has been using machine learning to identify where new boreholes should be located based on existing data and looking at that from an uncertainty standpoint. He did a very interesting presentation at the Midwest Geotech Conference. You can download that PowerPoint presentation from DIGGS website, diggsml.org. Just go in and look under presentations. You should find it. I've taken a couple of slides here from him to explain what they're doing. We're shifting away from the experience-driven paradigm to a deterministic paradigm where we can use all of this data that's available, whether it's from in situ testing, geophysical testing, traditional boreholes, and lab testing, to actually interpret and model the uncertainty within our site. So it's all driven by data. They used this model, or this approach, I should say, for a roadway redesign scenario where a bridge was being relocated something about 100 feet away from its existing location. And where did they need new boreholes? How many new boreholes were needed in order to help best target where the investigation effort should be. So in the past, on the left, it was all information because it's all report-based. It's all plan-based. Using your design software and engineering judgment, you end up with the result. The future trend is where it's a data-rich environment, using data interchange, using Python, learning algorithms, and your engineering judgment results in a knowledge-rich enabling AI design. We have another client that is actually using machine learning and AI for predicting deep foundation capacity and settlement. So this is kind of one of those scenarios where they're thinking totally outside the box, the AlphaGo master approach where let's use these other methods to have it predict how things are going to behave. People are using it for visualization purposes. So BGC engineering working with the HoloLens, which is augmented reality, so you can actually see your site model in augmented reality and explain it to other people, communicate with your colleagues. I definitely recommend watching that YouTube video. If you search for BGC Engineering and HoloLens, Scott Anderson gave a great talk about that at Geo Congress in Philadelphia about a year ago. So here's a visualization example from actually several years ago in Hong Kong. Every single one of those is actually a borehole or CPT sounding. Then they're adding all the BIM data, all the infrastructure data, all the deep foundations on any existing facilities, and looking at the tunnel alignment. So you can see a lot of boreholes there with all those different geologic units, all the deep foundation elements, tunnel alignments, everything. So you can use this for identifying conflicts, clash detection, where tunnels are going to run through building foundations or other infrastructure that are going to be problematic. So visualization is a big deal. All of those boreholes, other than the ones for the new project, which most of those are historical, all of those were imported from a standard data interchange format called AGS. So obviously that was for a large project. We did this case study with another client to indicate that they actually do this even on small projects. So this project I think only had about 10 boreholes. But that same visualization process that was done on that very large project can be done on that very small project. Once you have a standardized process and you're using data properly, it doesn't matter whether it's a project that has 10 boreholes or 2,000 boreholes. So here you see we've got our geologic units, got our boreholes shown there, and provides a nice way to visualize what does this geology look like for this particular site. It's all data-driven. In summary, what can we do with all of our data? Well, obviously, we can use our data to improve the data collection process, like we saw Braun Intertek was doing. We can improve visualization capabilities, as we've seen in those different 3D modeling examples. We can improve our communication using those visualization tools with our clients, with our colleagues, with the general public. We can improve our construction processes, our analyses and design processes. We can assess our vulnerabilities of our infrastructure better. We can reduce our costs, reduce our risk, reduce our uncertainty, increase our profitability, create better, safer, more cost-effective infrastructure, so we can fundamentally engineer better. That's what data allows you to do. All infrastructure projects rely on vast amounts of data. So some closing thoughts. Which of these benefits resonates with you? There are a lot of different reasons why we should be managing data, but it depends on what role you have. Are you an owner? Are you a contractor? Are you a consultant? Is your organization actually managing site investigation data and laboratory data effectively? And lastly, what is stopping your organization from using data interchange standards to improve your processes? Thank you very much. And if anybody would like to discuss how your organization can more effectively utilize data, feel free to reach out to me at sdeaton@dataforensics.net, and feel free to submit any questions to the forum. I look forward to hearing any comments, questions, and happy to respond to those. Thank you very much.